Okay, so we're going to look at the left and the right of functions, and we're going to use that to figure out what the y coordinates could be. But this time, they don't have to be the same on the left and the right. So this is x approaches c from the left. Okay, we already know that graphically. Now we're going to do it algebraically. X approaches c from the right side. Notice that in this particular notation example, they're both equal to L. So I'm going to give you some notation here. The 3 dots means therefore. It's like a conclusion. If the left limit and the right limit are the same, that implies that the limit as x approaches c is L. Notice how this combines the two statements. If A, then B, therefore C. Okay, the 3 dots means therefore the limit exists. Okay, so why would we need one-sided limits? Okay, think about your domain. Sometimes functions are not defined everywhere. They're only defined on a certain set of values. For example, consider that a business opened in 2007 with a total number of 15 stores. Write a limit statement to describe this situation. So we're going to say t equals 0 is for 2007. Would it make sense to approach 0 from both sides? No. No. Because the domain, where does that data start, is time greater than or equal to 0. Notice that this only exists to the right of 0. Okay, so I need to have a way to only look at a function from one side. Right? We don't always need both sides. Only exists to the right of 0. Okay, so what would that limit statement look like? Okay, the limit as t approaches 0 from the right of the function is, whoop, not 2007, 15. There you go. Is my T backwards? Yeah. I laugh because over here I did it right, but I've like always written my T's backwards. I don't know why. Okay. So here's the graph. Here's a piecewise definition. We're going to evaluate 2 limit statements. The limit as x approaches 2 from the left. Now I'm just going to say f of x, okay? Which part of the graph are you looking at? Okay, don't yell it. We have 1, 2, 3 steps. Don't yell it. Which portion should I highlight to look at 2 from the left? Kelly? The middle portion. 2 from the left. Yes. Okay. Which one of these pieces does it go with? What? The middle one. Okay. Right here. Go get a piece again. They're over there. You just feel free to open the tops. Okay, so 2 from the left. Look at the domain. X is less than 2. So I have the domain, algebraic definition. I have the graphical definition right here where I can see that clearly this is to the left of 2. So what is it approaching? 20. 20. Okay. What about the limit as x approaches 2 from the right? Okay. What parts don't yell it. What parts do I need to highlight on the graph and the function definition? And then what is the answer? Sammy?
The top line on the graph.
Okay.
And it's the third equation in the set.
Okay.
And so the answer is 22.
Yes. Okay. So 2 from the right. Okay, look at my arrow. So I'm approaching 2 from the right. Notice this happens to be an open circle. I'm going to put a little therefore. The limit as x approaches 2 of f of x. Don't yell it. What do I put in the blank? Yeah? Yes. Does not exist. They are not the same. Does not exist. Okay, so that's a piecewise definition. We're going to look at a set of piecewise functions, which is from the left and the right. And then we're going to look at some other things, like number 3. Okay, number 3 is a calculator question. We're not going to do it algebraically. Okay? So, we have graphical, tabular. Pick one of them and see if you can figure out how to find this limit. Do not do it algebraically. Just use a table or a graph. Okay, so we have consider a certificate of deposit that pays 10% initial deposit. There is your function. Okay, here is what A is. Okay, where X is the length of the compounding period. Okay. What do you think this represents? So use your calculator to estimate the following. Find the limit as x approaches 0 from the right, and I'll just plug in the function here. Yeah, well, obviously I can't plug in 0 because I end up with dividing by 0, which I can't do. So I need to 0 from the right. It's calculator, right? Either try to graph it and trace or use a table type function to figure out what this number could be. And let's say that 1 decimal place is appropriate. Right, there's right real context. Why do you need one-sided limits? Because sometimes both sides don't exist. Sometimes you don't want to approach from the left. It doesn't make sense to have a negative length. It doesn't make sense to have negative time values. Sometimes they're just different from the left and the right based on the situation. Okay, so now we're going to take away some of evaluate this algebraically. Okay, here we go. First one. Piecewise. Okay. Find both the left and right limit as x approaches 3. Okay. We're going to start with limit as x approaches 3 from the left. And I'm going to leave a little placeholder here. And I'm going to go to my function definition. And I'm just going to highlight this part here. Don't yell it. But which part do I highlight and why? You have to have the correct reason. Okay, Amanda?
Because 6x minus 4.
Because,
Because it's x is less than 3, so it's going for a negative sign.
it's coming from the left of 3. Grab a piece of candy. Yes. Okay, so instead of writing f of x, I'm going to copy over the actual equation that I need. Guys, one-sided limits, they're the exact same as regular limits. Just plug in the point. Check it. Plug in. Okay. Plug in the value.
Wait a minute. Example 1, B, C, and D, it says define it as x approaches 4, but it says but then it gives a completely different. Does the limit exist as x approaches something else?
That's a typo on my part.
Oh, man.
Sometimes it happens. Okay, so 6 times 3 minus 4. Isn't that how you find points on a graph? You just plug in the number. When we graphed piecewise, it didn't matter whether it was an open point or a closed point. It's just where the point was. Okay, so 18 minus 4. So the limit equals 14. Okay. Would that be an open or a closed point? Open, yeah. Open point at 3:14. It's okay. It's still the limit. I'm still tracing the graph there. Can I not add?
No, I was just wondering, is it open because...
Because it's less than 3. Yeah, open because it's less than 3. And we're going to sketch just a little picture to help us confirm graphically. Okay, now I need from the right the limit as x approaches 3 from the right. Okay, which would be the other part. Okay, because it's x is greater than 3. And so I'm going to copy that portion down. And I'm going to check the point. If the point exists, like that's it. There's nothing more to do. 3 squared is 9. Okay, so this is a regular point on the graph. Why do I know it's a closed point? Equal to 3. This is why we review all of that sort of simple graphing at the beginning, because it helps when you're trying to evaluate your limit. So 3. On the left of 3, I have a straight line, 6x minus 4. Sketch. I'm not really labeling the points here. Just a little sketch. All I'm going to do is check that endpoint, which would be at 3:14. Open. Positive sloped line to the left of 3. Okay? Notice that I have the endpoint labeled. Okay? X squared Could you graph this actually in your calculator? Yes, you could. But look at that. This one is at 9. This is not to scale. If I show you the graph, you're like, yeah, 14 and 9. But you need to be able to do it algebraically. If you need to confirm graphically, that is you. Yes?
Does it matter which point is open?
Graphically, yes. Limits, no. Right? Limits, the open and close doesn't actually matter. It just matters what you're tracing as you get there. But I'll highlight these portions. Okay, there's the yellow portion. See how it's less than 3? Open point. Okay? That's more for graphical. Okay? Here, the right of 3 is where the equals, that's where the closed point is. But open and closed points don't affect the limits. It's just what are you pointing at? I'm still pointing at it, whether or not it's open or closed. Okay, so find the left and the right. Okay, so I'm going to let you try this one. The limit as x approaches 4 from the left. Okay, the limit as x approaches 4 from the right. Yeah, I was actually about to just write this one in. Therefore, the limit does not exist, which I can tell very easily graphically, but 14 and 9 are not equal. Yes. Okay. I think this is going to be only see you once next week. What?
What's happening next week?
PSAT/senior activity. Yeah, Monday's a holiday. Wednesday's a senior thing. I see you guys next Friday.
Wait, what's a one? Do we have to go to school on PSAT day?
The seniors, you guys, seniors have a thing.
It's 9:30.
Okay, so the limit as x approaches 4 from the left is this one. So that's 8 minus 2x. Notice that I'm not writing f of x because f of x is split into pieces. And the first thing you always do for a limit is you check the point. So I plug in 4. It's not 3.9. I'm plugging in 4. That's how you find a point on the graph. This just happens to be an open point at 4, 0. Means as I trace the graph from the left side, I have a -2 slope like this. That's what this, oh, hold on. 4, I need to mark this, okay? So it means this. Right? I'm confirming graphically. This is what it looks like. There's an open point at 4, 0. From the right is this portion because x is greater than 4. Root x minus 4. Checking it by plugging in the point. 0. Okay, this happens to be, an open point because there is no equals at 4, 0. Well, that's a square root graph shifted right 4. Yeah. Does the limit exist? Therefore, the limit as x approaches 4, notice that I took off the left and the right. They are equal, means the limit is 0. Oh, this one's a good one. Okay. This is a little bit tricky of a definition. So I'm going to bring this domain down here, and I'm going to look at it. X not equal to 3. On a number line, it looks like this. Right? Everything but 3. Everything but 3. If I were to do interval notation, if I were to think of inequalities that mean everything but 3, I get x to the left of 3 and x to the right of 3. So this is the left and the right. It's just kind of hiding a little bit. This is the left and the right. It's both. X not equal to 3 means everything to the left of 3, everything to the right of 3. Okay, so we can do it separately. That's okay. But they're going to be the same. Okay? The limit as x approaches 3 from the left is the top portion. Now my first step is check, right? Plug in 3. The steps don't change with the limit statement. You still check it and then decide what to do next. So I get 0 over 0, okay? Factor and reduce because that's a polynomial. Okay, I'm just circling the things that are reducing so you can still see them. Okay, those two reduce. Plug in again. Okay, plug in 3, I get 6. I just know that graphically there's a hole. Okay, there's a hole at 3, 6 based on how the algebra worked out. Okay. Now, the limit as x approaches 3 from the right. Yeah, okay. Obviously, I still get 0 over 0 because I'm still just plugging in 3 to the exact same function. Okay, so I'm going to 3 from the right. Okay, so this reduces. I'm ready to plug in. I still get 6. Would you actually need to show me that twice? No. Maybe you have a little note over here that this is the left and the right, which is why you're only going to do it once, and you're like, oh, left and right. That's fine. Okay, so does the limit exist? Yes. The limit as x approaches 3 equals 6. What does it look like graphically? I know we're out of space a little bit. I'm just going to sketch a little picture. Okay. I know the hole is at 3, 6 because I found it. I'm left with x plus 3. It's just a straight line with an open hole in it. But what does this mean? Anyone know what that means? Ben?
There's just a dot at 3, 8.
Yeah, there's a dot at 3, 8. Yes, grab a piece of candy. Yeah, there's just a dot at 3, 8. That's a point. When x equals 3, y is 8. The limit is still 6. Notice how this portion here at actually x equals 3 had nothing to do with the limit. It's the left and the right side that has to deal with the limit. Okay, last question. Oh, absolute value. Can you write that as a piecewise for me before we actually try to find the limit? Yes, there is a purpose to every review worksheet you do. And it's right here. Write it as a piecewise. Okay. So I'm just graphing the top, and I'm just going to split it up based on that. X is less than 0. X is more than 0. Yeah, I do know these things reduce. That's okay. Okay, so I know absolute value is a piecewise function because half of it has a negative slope, half of it has a positive slope. And so I split it up. So I sketched the graph, right? That's what I did. I sketched the graph of this top portion and I split it into a piecewise. And then I just kept the divide by x there. I don't know what the whole thing looks like. I just know what the top looks like. And I use that to split it up into the left half with the negative slope and the right half with the positive slope. Okay, so I get -2, right? Because that's what it reduces to. And +2. Right, I'm doing it algebraically, and I did the piecewise part pretty quick because you should have done it 3 times. Evaluate the limit. The limit as x approaches 0 from the left. Well, to the left of 0, I get this. We will check it graphically to help confirm what we just did. There's nothing to plug in. It's just -2. The limit as x approaches 0 from the right. Okay, well on the right of 0, this reduced to +2. Check it by plugging in. Okay, therefore, the limit does not exist. All right, I'm going to go back to f of x because this is some piecewise definition. Does not exist. Okay, just pop it in your calculator, see what it looks like. Right? I don't know what to graph for that fraction, but I do know that absolute value 2x looks like this. And it sure looks like the x's should reduce. Usually they reduce, but this absolute value does something a little bit different. Okay. Math num absolute value. 2x divide by x. Oh, looks like a piecewise function where it's negative 2 on the left of 0, which I have, positive 2 on the right of 0, which I have. It's because the x's reduce, but the absolute value makes the signs change. All right, guys, that is it.